Okay, so this will be the second reaction out of chapter 11, second lecture out of chapter 11. Also reactions of alcohols. So in this lecture, we'll look at when alcohols react with sulfuric acid, they can undergo what's called dehydration. So that's if it's a secondary or tertiary alcohol. Or if it's a primary alcohol with sulfuric acid, you can use that to form an ether. They can also dehydrate to make alkenes, but you can also use that to make ethers. And then we'll look at a reaction, how to make esters from alcohols. All right, so we'll go through the basic mechanisms, how these reactions work. Okay, so if it's a secondary alcohol or tertiary, and you react this with sulfuric acid and heat, then this is basically going to do an E1 elimination. So if you remember from Organic 1 how an E1 mechanism works, so sulfuric acid is a strong acid, so acids donate protons, right? So anytime you see H2SO4, you can just think of it like H+. And so what's going to happen here, so you'll pick up a proton on the alcohol. Right, so now you have a good leaving group, and that's going to leave. So you make a carbocation, and then once you have the carbocation, you can lose a hydrogen. So let's sketch out hydrogen from the adjacent carbon. And then H2O molecule can take a hydrogen off, and the CH electrons can become a carbon-carbon double bond. And you would make the alkene. So of course you always have a choice of which alkene you could have made, because you could have took a hydrogen from this carbon so if you take a lone pair on oxygen, make a bond to that hydrogen, and the CH electrons from here could make a carbon-carbon double bond. And so you could have made one butene or two butene. And of course, since we made two butene, we could have also made the cis isomer or the trans isomer. And so which one are you going to make? You always make in this E1 elimination, the more substituted alkene and the more stable alkene. So the trans 2-butene would have been the major product. But you would expect to get a mixture of all three of these alkenes. So if we just take another example, and so let me show, let's see. So if we take this with H2SO4, so let me just show you how H2SO4 is working in this case. So that's a Lewis dot structure for H2SO4. Let's sketch out the OH bond. So again, H2SO4 is a strong acid, so you can lose a proton from H2SO4. And then water molecule can leave. Right, take the 2 electrons with it. So again, if you haven't had Organic 1 in a while, you want to get accustomed to writing mechanisms again. So notice the arrow originates on the bond, because that means we're taking those 2 electrons, and the arrowhead ends up on the oxygen. That means we're taking those 2 electrons and making a lone pair on oxygen. So now you would have, so H2O molecule left, and you have a carbocation there. So that carbon now is electron deficient, so it's positively charged. And so you want to remember Every time you make a carbocation, you want to look out for carbocation rearrangement. I didn't worry about it in this first example because I knew it wasn't going to rearrange. But in this example, it is going to rearrange, right? Because you make a secondary carbocation, so you always want to look, can it get to something better? Can it get to allylic, or can it get to benzylic? Or in this case, if it's secondary, can it get to tertiary? Or if it's primary, can it get to secondary or tertiary or allylic or benzylic? So in this case, it can, right? Because there's a hydrogen on the next carbon. If you move that hydrogen over to this carbon, then now you have a tertiary carbocation. And so now when you do the elimination, so it could be a water molecule that takes a hydrogen off, or you do now have HSO4 minus, right? Because in the first step, when H2SO4 lost a hydrogen, you created an HSO4 minus molecule. And so at this point then, you could lose a hydrogen from any carbon adjacent to the carbocation. So any of these hydrogens, and of course this position, if we call this A, is equivalent to that position, right? So you could lose a hydrogen from either of the A carbons, which is going to give the same product, or from B. So we could have made an alkene here if we lost it from carbon B, or if we lose a hydrogen from carbon A, we could have made that, which is equivalent to that. So which one is going to be the major product? Well, they're all tri-substituted alkenes. And so since these two are the same, it doesn't really make sense to keep talking about them both, but we will. Okay, so they're all tri-substituted alkenes, but having the double bond inside the ring is generally more stable than the double bond attached to the ring. So we're not going to form this one. Again, because the double bond external to the ring is not as stable as the double bond internal to a ring. So we're going to lose a hydrogen from one of the A carbons. So this could take a hydrogen from here. These electrons could become a carbon-carbon double bond, and now you satisfied the octet on the carbocation carbon. So that would give you your major product. And so if you notice, you remade H2SO4. So you use H2SO4 to start with, and then you got H2SO4 back at the end, so H2SO4 is not consumed in the course of the reaction, but it does facilitate the reaction. It makes it faster. Why does it make it faster? Because you produce a good leaving group. And so that makes making the carbocation a lot faster than if OH minus left by itself. So it speeds the reaction up, but it's not consumed in the reaction. That makes it a catalyst, right? So you don't need much H2SO4. You just put a drop or two in your reaction, and that's good enough to get it going. Although you would typically heat this reaction as well, right? Because heat tends to favor elimination. All right, so if you remember, that's what that symbol means. The triangle means typically heat in organic chemistry. Okay, so again, you have to watch out for carbocation rearrangement. So what if your alcohol is primary with H2SO4? So just to make drawing this mechanism simpler, we'll just consider H2SO4 as H+. So this is going to protonate. To make a water molecule, but this is not favored. Because it's a primary carbocation and very unstable. So what can happen instead with this primary alcohol is another alcohol can come in at this point and act as a nucleophile and kick off a water molecule. So now you have that, and then if this loses a hydrogen, right, then now you have an ether. Right, if you remember, ether is just an oxygen between two alkyl groups. So a way to simplify this reaction and make it easier to see the product. So let's just take two of the alcohols and draw them like mirror images of each other. So basically what happens in this reaction is you just lose a molecule of water, and this oxygen ends up attached to that oxygen. Right, and that's your ether product. But this is the mechanism. So this, since this is all happening at the same time, that's an SN2 reaction, right? And that avoids making an unstable carbocation. Although if you beat on this reaction enough, so if you did this at high temperature, then you could tend to do elimination instead. Okay, so let's see. So one more reaction in this lecture to look at. So if we take a carboxylic acid and an alcohol and a little bit of acid catalyst. So this could be any strong acid, just a drop or two, or if it's a liquid, or a little bit of a pinch or two if it's a solid, then this is going to make an ester. So this is what's known as a Fischer. Fischer esterification. And we won't look at the mechanism right now. We'll save the mechanism for the, we'll cover this in the carboxylic acid chapter. So we'll go through that mechanism in detail in that carboxylic acid chapter. So for now, we'll just look at how to predict the product. So if you see a carboxylic acid and an alcohol and an acid catalyst, predicting the product is easy. We're just going to lose OH from the carboxylic acid and H from the alcohol, and then this oxygen will end up attached to that carbon-oxygen double bond. Okay, so if we took another example, so if we had that carboxylic acid and this alcohol with acid catalyst, and then predicting the product is easy again, we're just going to lose H2O and then stick the alcohol in place of the oxygen, in place of the OH. And you would make that ester. Okay, so one more example. So if you did that reaction. So again, you have an alcohol and you have a carboxylic acid. Right, they just happen to be in the same molecule. So if you have an alcohol and a carboxylic acid and an acid catalyst, well, that's your recipe to make an ester. So since they're in the same molecule, so you're going to lose H and OH, and then this oxygen is going to end up attached to that carbon. So you're going to end up making a ring. And so anytime you make a ring in organic chemistry, I recommend you number so that you keep track of everything. So 1, 2, 3, 4, 5, 6. So that would be a 6-membered ring where oxygen is part of that ring. So if we draw a 6-membered ring, and oxygen is part of that ring, so we'll make one of these positions an oxygen, and we said oxygen was number 6. And then oxygen is going to be attached to number 1. So 1, 2, 3, 4, 5. So it doesn't matter which way you go, clockwise or counterclockwise in your numbering. But once we number everything, then we got to get everything else in the right spot. So carbon 1 is going to be a C double bond O. Carbon 2 and 3 and 4 are just CH2s, and carbon 5 has a methyl group on it. Right, so that would be your ester. It's just a cyclic ester in this case. And cyclic esters are called lactones. Okay, we'll stop there.